Welcome back to Sky Creative Channel. Ever wonder how the steel in America's trucks and factories is really made? Today we're taking you inside 4 incredible manufacturing facilities, from seamless steel tubes to the leaf springs under your truck. Let's dive in. Welcome back, folks. Today we're taking you inside one of the most fascinating manufacturing processes you'll ever see, the creation of seamless stainless steel tubes at Maxim Tubes. Now, if you're anything like me, you probably remember when steel manufacturing was all about brute force and sweat. But what we're witnessing here is a beautiful marriage of old-world metallurgy and cutting-edge precision engineering. Let me take you through this remarkable process. It all begins with solid stainless steel billets. These are cylindrical chunks of steel, typically heated to around 200 degrees Fahrenheit in a rotary hearth furnace. This isn't just any heating process. It's carefully controlled to ensure uniform temperature distribution throughout the billet. You see, back in the 1930s, the Germans perfected the Mannesmann process, which revolutionized seamless tube production, and we're still using refined versions of that brilliant innovation today. Once the billet reaches the perfect temperature, glowing that beautiful orange-red we all recognize, it moves to the piercing mill. This is where the magic truly begins. The piercing mill uses a mandrel, essentially a pointed rod, combined with angled rotating rolls. As the billet spins and moves forward, these rolls literally push the metal around the mandrel, creating the initial hollow form. It's called rotary piercing, and watching it work is like seeing butter being shaped, except this butter is 2000 degree steel. The precision required here is extraordinary. We're talking about tolerances within thousandths of an inch. Next comes the elongation process using a pilger mill or plug mill. This equipment features a reciprocating motion that gradually stretches and thins the tube wall, while maintaining perfect roundness. The tube passes over an internal mandrel, while external dies compress and shape it. It's a rhythmic, almost hypnotic process that reduces the wall thickness and increases the length simultaneously. This is where decades of engineering knowledge really shine. The die design, the reduction ratios, all calculated to prevent defects like cracks or dimensional variations. NTHE tube then moves through a series of sizing mills and stretch reducers. These machines fine-tune the outer diameter and wall thickness with incredible precision. Modern stretch reducers use multiple stands, sometimes up to 20, each making tiny adjustments. Computer-controlled systems monitor temperature, speed, and pressure in real time, something that would have seemed like science fiction to the old-timers who built America's steel industry. And heat treatment follows, where the tubes enter an annealing furnace. This controlled heating and cooling process relieves internal stresses and optimizes the metal's microstructure. For stainless steel, this typically means heating to around 900 degrees Fahrenheit, then cooling in a controlled atmosphere to prevent oxidation. This step is crucial for achieving the corrosion resistance and mechanical properties that make stainless steel so valuable. NTHE final stages involve straightening, where multi-roll straighteners remove any bowing or bending, followed by cutting to precise lengths using high-speed saws or laser cutting systems. Then comes inspection, both automated systems using ultrasonic testing and eddy current detection, plus good old-fashioned visual inspection by trained eyes. These tubes might end up in chemical plants, oil refineries, or even medical equipment, so quality control isn't negotiable. What strikes me most about this process is how it represents the evolution of American manufacturing values, that combination of innovation, precision, and reliability that built this nation's industrial might. Now let's head across the pond to the British countryside, where Marshall Trailers has been building agricultural trailers since 1948. That's right, this family-run company has been at it for over 75 years, and watching their production process is like witnessing a masterclass in agricultural engineering. For those of us who remember when farming was done with simpler equipment, this is going to be a real treat. An NTHE process begins in the cutting department, where heavy-gauge steel sheets and structural steel sections arrive. Marshall uses advanced CNC plasma cutting tables and laser cutting systems to cut components with precision. These machines are programmed with CAD designs, allowing them to cut complex shapes from steel plate, ranging from quarter-inch up to half-inch thickness. The laser cutters use focused beams that can slice through steel like it's paper, with cutting speeds up to 400 inches per minute. The accuracy is within 0.1 millimeters. That's about the thickness of a human hair. Next, we move to the bending and forming section. Here, hydraulic press brakes, some with capacities exceeding 300 tons, shape the steel components. The trailer sides, for instance, are formed from single pieces of steel using precision dies. The operators, many who've been with Marshall for decades, position the steel, and the press brakes back gauge system ensures perfect alignment. Modern press brakes feature CNC controls that adjust bend angles automatically, compensating for material springback, which is the tendency of metal to partially return to its original shape. NTHE chassis fabrication is where things get really interesting. Marshall builds their trailer frames using high-strength rectangular and I-beam steel sections. These components are positioned on large welding jigs, essentially giant fixtures that hold everything in perfect alignment. The welding process primarily uses MIG welding, where a continuous wire electrode feeds through the welding gun, creating strong, clean welds. Some critical stress points receive TIG welding for even greater strength and precision. The welders move methodically, laying down beads that will hold these trailers together through decades of hard farm work. One fascinating aspect is their hydraulic system installation. These trailers feature sophisticated hydraulic tipping mechanisms that allow farmers to dump loads efficiently. The hydraulic rams, massive telescoping cylinders, are mounted beneath the trailer bed. These systems can lift loads exceeding 20 tons at angles up to 60 degrees. The hydraulic power unit, typically driven by the tractor's PTO or a separate hydraulic system, pushes oil through hardened steel cylinders at pressures around 3,000 psi. Safety valves and flow controls ensure smooth, controlled tipping operation. NTHE axle and suspension assembly comes next. Marshall uses heavy-duty axles, often tandem or triple configurations, rated for road speeds and heavy loads. The suspension typically features either leaf springs or, in premium models, air suspension systems. Leaf springs, those curved steel strips stacked together, provide both support and shock absorption through their flexing action. Modern air suspension systems use rubber airbags that can be adjusted for different load conditions, providing a smoother ride and better weight distribution. NTHE bodywork phase involves fitting the trailer sides, which often feature extensions for increased capacity. These sides are mounted on heavy-duty hinges with quick-release mechanisms, allowing farmers to remove them for different applications. The tailgate incorporates grain-tight seals and heavy-duty latches. NSUR face preparation and coating are critical for longevity. All trailers undergo shot blasting to remove mill scale and contaminants, creating an ideal surface for paint adhesion. They're then treated with zinc-rich primer and finished with polyurethane topcoats that resist UV degradation, chemical exposure, and mechanical damage. Some components receive hot dip galvanizing for ultimate corrosion protection, a process where steel is immersed in molten zinc at 840 degrees Fahrenheit. NTHE final assembly brings everything together: brake systems with automatic slack adjusters, LED road lights complying with UK regulations, mudguards, and registration plates. And what makes Marshall special is their attention to farmer feedback. They've refined their designs through decades of real-world use, creating trailers that genuinely serve the agricultural community. It's that kind of dedication to craft and customer that reminds me of America's own heritage of quality manufacturing. Alright folks, now we're diving into something that's been under virtually every truck, trailer, and heavy vehicle for over a century: the leaf spring. Wondee Autopart has mastered the art and science of producing these crucial suspension components, and I've got to tell you, watching this process unfold is absolutely fascinating. For those of us who've worked on vehicles over the years, understanding how these springs are made gives you a whole new appreciation for the engineering underneath. And Wondee begins with high-grade spring steel, typically SAE 5160 or 9260 alloy steel. These aren't ordinary steels. They contain precise amounts of chromium, silicon, and other elements that give them the unique property of elastic memory. The raw material arrives as coiled steel strips in various widths and thicknesses, usually ranging from quarter-inch to half-inch thick, and 2 to 4 inches wide. NTHE first major operation is cutting. Wondee uses hydraulic shearing machines and CNC cutting systems to slice the steel strips to precise lengths. Each leaf in a spring pack has a specific length, the main leaf being the longest, with progressively shorter leaves stacked above it. The cutting tolerance is critical, typically within 1/16 of an inch, because any variation affects the spring's load-carrying characteristics and stress distribution. Next comes one of the most distinctive operations, eye forming. The ends of the main leaf, and sometimes the second leaf, need eyes, those circular loops that attach to the vehicle frame and shackles. This is accomplished using specialized eye-forming machines. The steel end is heated to approximately 1,600 degrees Fahrenheit using induction heating coils. Once it reaches the proper temperature, glowing bright orange, the heated end is wrapped around a mandrel by hydraulic rams. The pressure is tremendous, around 100 tons, forcing the hot steel to bend without cracking. The formed eye is then cooled and ready for the next process. Now we move to cambering, which creates the characteristic curve of the leaf spring. Flat leaves are loaded into cambering presses, where they're heated and bent to a precise arc. This curvature is essential. It's what allows the spring to flex and absorb road shocks while supporting weight. The camber radius is calculated based on the intended load capacity and desired ride characteristics. Wondee uses computer-controlled cambering systems that monitor temperature and apply pressure gradually, ensuring consistent results across thousands of springs. NTHE heat treatment process is where leaf springs gain their legendary strength and resilience. The leaves are loaded into continuous heat treatment furnaces, operating at around 1,550 to 1,650 degrees Fahrenheit. This austenitizing process transforms the steel's crystalline structure. After sufficient time at temperature, usually 20 to 30 minutes, the leaves are rapidly quenched in oil baths. This quenching locks in a very hard but brittle martensitic structure. But here's the clever part. That's too hard for practical use. So the springs immediately go into tempering furnaces at lower temperatures, around 800 to 900 degrees Fahrenheit. This tempering process is the secret sauce. It relieves internal stresses and adjusts the hardness to achieve the perfect balance between strength and flexibility. Hold it too long or too hot and you get soft springs that sag. Too little tempering and they'll be brittle and crack under stress. Wondee's metallurgists have perfected these parameters through years of experience and testing. NSHOT peening comes next, and this is a process that really showcases modern manufacturing sophistication. The springs are bombarded with small steel balls traveling at high velocity in enclosed tumbling chambers. Each impact creates a tiny dimple on the surface, inducing compressive stresses in the outer layer of the metal. This might sound counterintuitive, but these compressive stresses actually prevent crack initiation and propagation, dramatically improving fatigue life. A properly shot peened leaf spring can last twice as long as an untreated one. NSUR face coating follows shot peening. Wondee applies protective coatings through various methods. Some springs receive powder coating, where electrostatically charged powder particles adhere to the metal surface, then are cured in ovens at around 400 degrees Fahrenheit. This creates a durable, chip-resistant finish. Other springs get hot-dip galvanizing or specialized epoxy coatings for maximum corrosion protection in harsh environments. An assembly is where individual leaves come together into a spring pack. The leaves are stacked in graduated lengths and aligned precisely. Center bolts pass through pre-drilled holes holding the pack together. These bolts are torqued to exact specifications. Too loose and the leaves slide against each other excessively. Too tight and they can't articulate properly. Spring clips are installed at strategic points along the pack to prevent leaf separation, while still allowing the necessary relative motion during flexing. NEND fittings are attached next. The eyes receive bushings, either bronze, rubber, or polyurethane, depending on the application. These bushings provide a bearing surface and isolate vibration. Some heavy-duty springs get additional components like wraparound fixtures, helper springs, or progressive rate designs, where additional leaves engage only under heavy loads. What impresses me most is how this seemingly simple component, just layers of curved steel, embodies so much engineering knowledge. From the chemistry of the steel alloys to the physics of stress distribution, from heat treatment metallurgy to surface engineering, every step reflects decades of accumulated wisdom. And companies like Wondee keep this crucial technology advancing, supporting transportation and commerce worldwide. For our final segment today, we're looking at something that might not seem glamorous at first glance, but represents an absolutely critical link in global commerce: steel drum manufacturing at Yingkou Bohai Machinery. And Yingkou Bohai's production line starts with steel sheet coils, typically cold-rolled steel ranging from 0.8 to 1.2 millimeters thick. These massive coils, weighing several tons each, are mounted on decoiling machines, motorized mandrels that rotate, feeding sheet metal into the production line at controlled speeds. Tension rollers and edge guides keep the material tracking straight and prevent buckling or waviness. NTHE, first forming station, cuts body blanks, rectangular pieces that will become the cylindrical drum body. Modern shearing systems use hydraulic or mechanical presses with hardened steel blades. The cutting action is precise, with minimal burr formation. The blank dimensions are critical because they determine the drum's final diameter when rolled into a cylinder. Next, the blanks move to edge preparation equipment. The long edges that will be welded together get beveled or cleaned using grinding wheels or milling cutters. This prepares them for welding by removing any oil, rust, or mill scale that might compromise weld quality. Some systems use plasma or laser cleaning for this operation. NTHE cylinder forming process is where flat steel transforms into round drums. 3-roll or 4-roll plate bending machines accomplish this. The blank feeds between large diameter rollers. The top roll presses down while bottom rolls rotate, gradually curling the sheet into a cylinder. The operator monitors the curvature, making adjustments until the edges meet perfectly. This requires skill and experience, because different steel batches and thicknesses behave differently during forming. End-seam welding is perhaps the most critical operation. Yingkou Bohai typically employs automated MIG welding systems, or resistance seam welding. With MIG welding, the two edges are clamped together and a welding head travels along the seam, laying down a continuous bead. The wire feed rate, voltage, and travel speed are all precisely controlled to ensure complete penetration without burn-through. Modern systems use weld monitoring sensors that detect defects in real time. Resistance seam welding, alternatively, uses copper electrode wheels that roll along the joint, passing high electrical current through the material. The resistance heating melts the steel locally, creating a continuous weld. This method is extremely fast and produces very consistent results. After welding, the body seam typically undergoes grinding to smooth any excess weld material and create a clean, uniform surface. Automated grinders with spring-loaded wheels follow the contour of the drum, removing high spots without gouging the base material. And meanwhile, drum ends, the top and bottom circular pieces, are being manufactured on parallel equipment. These start as flat circular blanks cut from sheet steel using turret punch presses or laser cutters. The blanks then move to progressive stamping presses, where multiple forming operations happen in sequence. First, a shallow flange is formed around the perimeter. Then rolling ribs are formed. These concentric rings add tremendous strength, preventing the ends from deforming under pressure or when drums are stacked. The geometry of these ribs is carefully engineered. Each ring increases rigidity exponentially. NTHE's center opening for the bung, the threaded opening where caps attach, is formed using punch and die sets. The metal is drawn up, creating a neck that's then tapped with threads. Some systems form multiple features simultaneously using compound dies that combine several operations in one press stroke. End chime formation is another crucial step. The chime is that rolled edge around the top and bottom of the drum that provides handling strength and sealing surface. Sheet metal edges are folded over mandrels and crimped multiple times, creating a thick, reinforced rim. This rolling operation requires substantial force. Hydraulic chiming machines exert several tons of pressure to form these heavy-duty edges. An assembly brings the body and ends together. The drum body is positioned vertically, and end pieces are placed in position. Double seaming machines then join them. This process rolls the chime of the end piece and the edge of the body together, creating a mechanically interlocked joint. First, the seaming chuck rotates, while a roller gradually folds the edges together in what's called the first operation seam. Then a second pass tightens and compresses this joint in the second operation seam. The finished double seam is incredibly strong and, when properly formed, completely leak-proof. Seam inspection is critical. Operators use seam inspection gauges to measure thickness, length, and quality of the seam cross-section. NNSUR face treatment and coating represent the final major operations. Drums first undergo phosphate coating. They're immersed in or sprayed with phosphoric acid solutions that chemically react with the steel surface, creating a crystalline zinc or iron phosphate layer. This layer dramatically improves paint adhesion and provides corrosion resistance. After phosphating and rinsing, drums enter paint lines where they receive internal and external coatings. Spray guns or electrostatic coating systems apply epoxy, phenolic, or polyurethane-based paints. These coatings must resist chemical attack, UV degradation, and mechanical damage. Curing ovens then bake the painted drums at temperatures around 350 degrees Fahrenheit, cross-linking the paint molecules into a tough, durable finish. What strikes me about this entire process is how it exemplifies industrial efficiency perfected over a century. Every operation has been refined through millions of drums produced, every machine optimized through generations of engineering improvement. These humble steel drums, storing everything from chemicals to food products, from lubricants to pharmaceuticals, represent a manufacturing achievement we often take for granted, but absolutely depend upon.